Okay, ladies and gentlemen, here we have an example that is of a student who slides a 2,000 Newton crate across the floor by pulling with a force of 750 newtons at an angle of 30 degrees with the horizontal. If the crate moves with constant speed, find the coefficient of kinetic friction between the crate and the floor. Okay? So what we've got here, let's do an actual diagram of this just to make sure we're all on the same page. We've got a crate. Right? And then the student is pulling the crate with a 750 Newton force at an angle of 30 degrees from the horizontal. Alright? So what we've got here is the crate. Now normally when the crate was being pushed, it was pushed horizontally, and it was very easy to see that the force of friction was related to the normal force, which was equal to the weight. At this point here, though, there is some component, there's a vertical component of the pull of the person, of this student. There's a vertical component of it that is sort of helping out the ground. So in this case, the ground doesn't have to do all of the force to counteract the force of gravity on the crate, which means that the normal force is going to be less than the weight of the object. So let's see what this looks like as a free body diagram. So here we'll have our crate. We'll have the weight of that crate like so, which we know will be equal to the crate's mass times the acceleration due to gravity, although they gave us 2,000 newtons already, so we don't even need mg at all for that. Now, we've already said that the normal force does not have to be equal to the weight of the object, because the force that the student exerts is going to have a vertical component to it. Right, so there's F of P, and then the force of friction, well, if it is moving at constant speed, we'll see that there is a horizontal component of the pull that force of friction has to just balance. So we'll have the force of friction like so. This here is going to be a semi-accurate free body diagram. Okay, I'm going to mess this free body diagram up right now. I'm going to do so by adding the components of the force of the pull. So there's the x component. And there's the y component of the pull. Doing this just to see what goes better in the positive x and y directions, respectively. Okay, so at this point it's time to set up our equations and see what we get. Well, we know that the force of friction is equal to mu k times the normal force. And mu k is what we were asked to find, so we want to start off with the x direction and find out what's happening there. So taking the sum of the forces in the x direction, we'll have the fpx in the positive direction, and the force of friction in the negative direction. Now, we know that the object is not accelerating, so we know these have to be balanced. We know that the sum of the forces in that case has to be 0. So we've got 0 equals fpx minus, we also know that the force of friction is mu k times the normal force. And we can see that mu k times the normal force then is equal to the x component of the pull. And if we're going to find just mu k on its own, we'll have the x component of the pull divided by the normal force. Well, the x component of the pull is no real problem because we know that theta is equal to 30 degrees. We know the magnitude of the force is equal to 750 newtons. So we can get that easily enough right there. It's the normal force that we have to get at this point. So when we're trying to find the normal force, we're going to have a new set of equations for what's happening in the y direction. So, the sum of the forces in the y direction, well, we've got the normal force upwards, as usual, but now we also have this y component of the pull. And we're going to subtract from that the weight being in the negative direction in this case. Once again, the crate is not accelerating up or down, so the sum of the forces has to be 0. So we've got the normal force plus the y component of the pull minus the weight. And if we solve this for the normal force, we're subtracting Fpy from both sides and adding the weight to both sides. We'll see that the normal force is equal to the weight minus Fpy. So we can see clearly from this that the normal force is no longer equal to the weight. It is less than the weight because we're subtracting the magnitude of the y component of the force in this case. Now we know this. Let's just kind of insert what Fpy is. We know that the normal force is equal to the weight minus the magnitude of the force of the pull times sine of theta in this case. And we can now insert this into our equation here. While I'm doing so, I am going to make that into its component form. All right, so we're going to have mu k is equal to Fp cosine of theta divided by the normal force, which is the weight, minus Fp sine of theta. At this point, knowing Fp and theta and the weight, we can put our values in and we will get a value of about 0.39997 something. So we'll take that up to about 0.4 for the coefficient of friction. Et voilà, voici la réponse.